Hi everyone! In today's video we're going to continue our discussion of hybridized orbitals. So last time we looked at sp3 hybrid orbitals, and we said that they kind of look like balloons. They look like this. They're kind of sort of halfway between an s orbital and a p orbital. So remember, this has 75% p character and 25% s character. And the whole reason that we have these hybrid orbitals is to explain bonding in molecules for certain situations that don't really make sense otherwise. So as an example, we looked at methane. And we looked at the unhybridized energy diagram for carbon, and we saw that there were only 2 unpaired electrons. So we said, okay, we have to come up with a different way of explaining how carbon bonds, because it should have 4 unpaired electrons. It can make 4 bonds. So that's where these hybrid orbitals came from. So we also saw that for methane, if we put those 4 sp3 hybrid orbitals that were created into the same space, we get, let me get a different color here. We get something that looks like this, and then there's kind of one back here as well. So 2 of those orbitals are in the plane of the paper, and then 2 are going back and forth. So one's going behind, one's coming out towards us. And then we also have 4 unpaired electrons. So I'll just draw some unpaired electrons in each of these sp3 orbitals. So red is sp3. And then we have our 4 hydrogen atoms in methane, and those are each going to be, or each of those have 1 electron in a 1s orbital. So we're going to start making some bonds and pairing up some electrons. And they have to have opposite spin. Okay, so this is our methane molecule. We have 4 sp3 hybrid orbitals coming from carbon, and those are each bonding with a 1s hydrogen orbital. And then we also said that each of these pairs of electrons are going to exist in a bonding orbital. So remember, we talked about molecular orbitals. And this is going to form a single bond, also called a sigma bond. And we use the Greek letter sigma for that. Okay, now what about molecules that have a double bond? How does that work? So let's look at another molecule, ethylene. So ethylene has 2 carbons and 4 hydrogens. So let's actually start by drawing the Lewis structure just to kind of see what types of bonds we're expecting. So we do have 2 carbons, so those will probably go in the middle. And again, each of those carbons will have 4 valence electrons that are unpaired. So we'll make a bond here between those 2 central atoms. And then we have 4 hydrogens, And remember, molecules like to be pretty symmetrical, so I'm going to divide those hydrogens evenly between the two carbons. So I'll put two hydrogens here on the first carbon, and then two hydrogens on the second carbon. All right, now we can start pairing up electrons, but we still have unpaired electrons on those carbons. So I'm going to pair those together and make a double bond between the carbons. So I'm going to erase these two and make them into a double bond. Oops. What just happened? Oh, there it is. Okay, so how do we explain this Lewis structure using hybrid orbitals? Well, let's start by trying to figure out the steric number for each carbon. So let's just look at this first carbon. How many bonded atoms are attached to that carbon? 3, right? We have 2 hydrogens and another carbon. And let's highlight those just to make it very clear. So those are the 3 bonded atoms or bonded groups. So that means that we have a steric number of 3. And do you remember which hybridized orbital corresponds to a steric number of 3? Is it sp, sp2, or sp3? sp2. Okay, so that's also the same for the other carbon. It's also bonded to 3 other atoms, so it is also sp2. Okay, so let's kind of figure out now how we can explain this type of bonding. So let's just refresh our memories on the unhybridized energy diagram for carbon. Okay, so this is the unhybridized energy diagram for carbon. There are only 2 unpaired electrons, and that doesn't quite make sense here. So let's again combine our orbitals, but this time we're only going to combine the 2s and then 2 of the 2p orbitals. So one of those 2p orbitals doesn't have an electron, and we don't really need it in this case, so we're just going to kind of let it hang out on its own. All right. Now, if we just combine those, so let's hybridize. What we end up with are 3 sp2 hybrid orbitals, and then we have a leftover 2p orbital. Okay, so now we can place those 4 electrons, or well, first let's put our 1s electrons down here, but then we can place those 4 electrons in our unhybridized atomic orbital diagram into their own spaces. Okay, so now we have 3 unpaired electrons in an sp2 orbital, and then we have 1 unpaired electron in a 2p orbital. Okay, so what is this going to look like? So sp2 orbitals also kind of look like an sp3 orbital, a little bit different, but an let's see, there we go. So an sp2 hybrid orbital has less P character and more S character uh, than an sp3 orbital. So it's approximately 60% P character and approximately 30% S character. Let's just say that for now. Okay. That doesn't add up to 100, but you get the idea. It's about a third S character and 2/3 P character. I haven't had enough coffee yet. All right. So now let's draw what this looks like. Okay, so we've got our 2 carbons in our ethylene compound, and they each have 3 sp2 hybrid orbitals. Now, those hybrid orbitals are going to try to get as far apart from each other as possible, so they'll have about 120 degrees between them. So it's going to look something like this. And I'm going to draw the 2 in the middle overlapping. Okay, so again, we've got 120 degrees here between all of these bonds. Oh, actually, let me erase this because I actually need that space. So I'll just draw it over here. Now, we do have a p orbital left over. So remember, on the previous slide, we saw that there's a p orbital left over right here. Okay, so that means each of these carbons has a p orbital, and we're going to draw that going up and down. And I'll draw a little key off to the side. Okay, so remember, we have a single electron in each of our sp2 orbitals. Oh, let me draw this a little better here in the middle. I want to make sure we have enough room to show the pair of electrons. There we go. So those 2 carbon atoms have 2 electrons that are pairing up to create a bond. And remember, we also have an electron hanging out in the p orbital on each carbon. Okay. So each of the sp2 hybrid orbitals that are left over is going to bond with a hydrogen. Okay, so we're going to draw our hydrogens in green. Okay, so those are our carbon-hydrogen bonds. Now, what about those p orbitals? What are those going to do? Well, they are side by side, and they each have an unpaired electron. So we're going to form a pi bond. And actually, the p orbitals will overlap kind of above and below the carbons, and that is our double bond. So that's called a pi bond. Now, this kind of makes it look like we have a triple bond, but we don't. It's still just a double bond. So if we look back at our Lewis structure, this is our p orbital overlap. Oh, overlap. So that second bond is the pi bond. Okay. So now I'm also going to label each of the single bonds as sigma bonds. And you should get in the habit of doing this on quizzes and exams because you do want to indicate what type of bond you have. Oh, and I actually noticed I should have drawn this electron as a spin down electron because otherwise they won't pair. Okay. Okay, so this is how we use hybrid orbitals to explain double bonds. Again, we have 3 sp2 hybrid orbitals and 1 2p orbital that's just left over, but also has an unpaired electron that can then make a double bond. Okay, now what about triple bonds? So let's look at another molecule. This one's called acetylene, C2H2. So let's draw the Lewis structure first. So we have 2 carbons again, so those will go in the middle, and they each have 4 valence electrons. Oh, I have a random mark over there. And then we have 2 hydrogens. So I'll give each carbon 1 hydrogen just to make it symmetrical. All right, so now we can start making some covalent bonds. But each carbon still has 2 unpaired electrons. And we could pair them up to make them lone pairs, but carbon doesn't like to have lone pairs of electrons. So instead, we can make those into a triple bond. Okay. So now how do we explain this using our hybridized orbitals? So let's first identify the hybridization of each carbon using its steric number. So if we focus on just one of these carbons, so the carbon on the left, how many bonded atoms are connected to it? 2. So we've got a steric number of 2. So now is that sp hybridized, sp2 hybridized, or sp3 hybridized? It's sp hybridized. Great. Okay, so now let's also compare energy orbital diagrams here for the unhybridized carbon versus the hybridized carbon. Okay, so we've got our unhybridized carbon atomic orbital diagram there. And this time, we're just going to combine this 2s orbital with one of the 2p orbitals. Okay, so now we're going to use our magic hybridized powers. And we're going to create 2 hybridized sp orbitals from those 2 orbitals I highlighted in yellow. And then we have 2 leftover p orbitals. Now, we're still going to give all 4 of those electrons in energy level 2 their own space. So we'll have 1 unpaired electron in each of those 4 orbitals. So we have 2 unpaired electrons in the sp orbitals, the sp hybridized orbitals, and then 2 unpaired electrons in the 2p orbitals. Okay. So now let's see what that looks like in terms of our acetylene molecule. All right, so what do these orbitals look like? Well, we combined an S and a P, so that will give us our SP, and I'm going to draw it kind of funny because it has 50% P character and 50% S character. So it looks a little weird, but if we then try to kind of piece together our molecule here, each carbon will have 2 sp hybrid orbitals. So they're going to try to get as far apart as possible, which means they'll have a bond angle of 180 degrees. Oops, I drew that in the wrong place. There we go. And that makes sense, right? If we look back at our Lewis structure, we have a 180 degree angle between bonds. Let's see. Now each sp hybrid orbital has an unpaired electron. So those will pair up in between the carbons to create a sigma bond. But then we also have, if we look at our hybrid orbital diagram, we have 2p orbitals. Okay, so where will those go? Well, they're going to position themselves, and actually let me get rid of this angle. They're going to position themselves as far apart as possible as well. So one will face up and down, and then the other will be 90 degrees from that. So it's going to come out and back. So I'll just make that clear here, 90 degrees. All right, and that's going to be true for each carbon. And I'm just drawing them in different colors so you can kind of see them separately from each other. And then this is our little legend off to the side. Okay, now each of those p orbitals has an unpaired electron. And it doesn't really matter if they're in the upper lobe or the bottom lobe, because we don't really know where it is at any given moment. We just know that it's somewhere in that space, right? So it could be above the carbon, it could be below the carbon. But what ends up happening is when we form this pi bond between the two carbons, the electron density kind of spreads out. So we almost have like a little cloud hanging out above and below the molecule. So it doesn't really matter where the electron is, but in our two-dimensional drawing, I just show them at the top just for simplicity. So actually, let me show you what it kind of looks like. So we would have a sigma bond in the center, and then there's just this like cloud of electrons above and below for this pi bond. So we don't really know where those electrons exactly are. And then we also have unpaired electrons in the p orbitals that are 90 degrees from the other p orbitals. And these are also going to form pi bonds. or a pi bond, excuse me. And so that will also show up as like a cloud kind of in front of and then maybe behind the molecule. So it almost looks like you have hot dog buns just kind of surrounding the carbons. There's one on top, one on bottom, and then there's one in front and one behind. So that's what those pi bonds look like. All right, so now the last thing we're missing is the hydrogens. So we have two hydrogens, and I'm going to show those in green again. And remember, they have 1s orbitals because they have one electron each. So the only place to really pair them up is with these sp orbitals on either end. So now we have our full acetylene molecule, and we have a triple bond. So if we go back to our Lewis structure, I just want to kind of show you that we have within that triple bond a sigma, a pi, and a pi. And those are our bonds that are making up the triple bond. All right, so all of this is really complex, right? But this is just how we explain the type of bonding that we see in different molecules. We use these hybrid orbitals in order to do that. Oh, and I forgot to label my carbon-hydrogen bonds. So those would also be sigma bonds. So don't forget those sigma and pi bonds. Now, I do have a question for you looking at this molecule. Can we spin the carbons? So like, could we rotate them like tires almost? No. So if we tried to spin one of the carbons but keep the other one stationary, it would break those pi bonds, and you need energy in order to do that. So without any energy, those bonds will be static. They're not going to rotate. Now, what about our double bond? Can we rotate either of those carbons? No, because again, we'd be breaking that pi bond. So those are going to stay parallel to each other. But then what about, what about if we just had a sigma bond? So let's ignore the pi bonds there. Could we rotate the carbons? Yeah, so if we just had a single bond between those carbons, we could totally rotate them. We could rotate them any way we want. But once you start adding in double and triple bonds, you can no longer rotate those carbons. And that will be important later on because that's going to dictate where certain bonds are in relation to each other. So just keep that in mind. You cannot rotate double bonds or triple bonds, or else they would break. Okay, so let's just summarize everything we've learned in the last couple of videos. So, let's see. So let's start by discussing P character. How much P character does an sp hybridized orbital have? Well, there's one s and one p, so if we split it in half, we've got 50% P character. What about an sp2 hybridized orbital? How much P character do we have? And I'll be more exact here. We have 67%. And then what about our sp3 hybrid orbital? How much p character does that have? 75%. That one's a little easier. Okay, so now what about length? So which hybrid orbital do you think is the longest? So it would be the sp3 orbital. So that is the longest one. And that makes sense, right? If we think about s orbitals being spherical and p orbitals being more elongated, the sp3 hybrid orbitals have the most p character, so they would be the longest. The other way you can think about this is that an sp3 hybrid carbon only forms single bonds, and those are the longest bonds. So then, using that same logic, which hybrid orbital has the shortest length? sp. It has the least amount of p character, so it is the shortest, but that also makes sense because triple bonds are short. And then in the middle we have our double bonds, and those are just kind of in between. Okay, now let's use some data to back this up. So acetylene, which we just looked at, and I'm going to use a different color here. So acetylene had the triple bond, right? It has a bond length of 1.2 angstroms. So angstroms are related to meters, if that helps you kind of visualize what that is. It's a really small unit, but it's related to meters. And then ethylene, which had a double bond, its bond length is 1.34 angstroms. And then ethane, which has single bonds, that has a bond length of 1.54 angstroms. So you can see that triple bonds are the shortest bonds and single bonds are the longest bonds. All right, and then bond energy. Let's talk about how much energy it takes in order to break apart a triple bond versus a double bond versus a single bond. So for acetylene, it takes 820 kilojoules per mole to break apart its triple bond. For ethylene, it takes 632 kilojoules per mole to break apart its double bond. And then for ethane, it takes 368 kilojoules per mole to break apart its single bond. So we can see that triple bonds are the strongest, which makes sense, right? We have 3 bonds there. That provides a little more security. And then single bonds are less strong. They don't need as much energy to break apart. Okay. So if you want to get some more practice with SP, SP2, and SP3, definitely try the Skill Builder 1.7 exercise on page 23. And I would recommend this to everyone because this is tough stuff and we are going to use this in the future. So we're not really reviewing it and forgetting it. We are going to use this throughout organic chemistry. Okay, so I will let you review that material and get some practice in. And in the next video, we'll talk about polarity and intermolecular forces. I will see you then.